Okay, I can do
Thank you.
that. So, hello everyone. Welcome to this candidate talk. So, today we have Dr. Chen from University of North Carolina, and he's not new to UCF. He has been here for a couple of years. He was doing a postdoc with Dr. Shah, I think, from 2015 to 2017,
Yep.
and so he will talk about his recent work in adaptive efficient deep neural networks. So, why don't you start, Chen?
Okay. All right. Thank you, Dr. Roa, for the introduction. Good morning, everyone. My name is Chen. I'm currently assistant professor at ECE department at the University of North Carolina at Charlotte. Unfortunately, due to the pandemic, we have to reduce the travel. Otherwise, I would love to visit UCF and enjoy some of the nice weather there. We'll be raining a couple of days here in Charlotte area. So for today, I'm going to talk about our recent work on adaptive and efficient deep neural networks for edge computing. As we all witnessed, there's been great success in deep neural networks for various vision applications and other research domains. So since the invention of AlexNet in 2012, there's a lot of deep neural networks have been developed with stronger modeling capacities, but at the same time, the computational cost also increased significantly, as you can see from these vertical axes here, measured by the floating point operations, the flops. So just to give you another concrete example, this table provide a side-by-side comparison of a couple of very popular deep neural network models. As for example, for this VGG16 network, as you can see here, it has 138 millions of parameters or model weights, and also occupies 15.5 gigaflops. So that's a lot of memory and computational cost. But in our real world applications, we have a lot of smart edge devices or IoT devices, right? Like the mobile phones, the surveillance cameras that are being deployed in the city scale, like the traffic conjunctions to monitoring the traffic, etc. But these smart edge devices don't have powerful resource. So they usually have limited resource in terms of compute. So that means a lot of deep neural networks is not able to run on these edge devices. So we have to develop those edge-friendly neural networks so that it can be efficiently deployed on these smart devices. So towards these efficient neural network design, there's a couple of very popular directions. So the first one is the network pruning. So for network, maybe we can remove or prune some of the neurons in the network. Maybe some of the neurons, they are redundant. They function the same way. So we can remove some of the neurons so we can reduce the compute, but at the same time, we may able to maintain the same accuracy. So that's the network pruning methodology. So another direction is we can design some of the efficient network architectures that requires to maybe modify some of the operations in the conventional deep neural networks. For example, these mobile nets family networks, they devise these depth-wise separable convolutions to facilitate the computation efficiency. And also the other one, for example, the adder nets, they remove the multiplication in the conventional convolutional operation, rather just using purely addition to reduce the compute. And the third direction is we can reduce the precision of the network. Typically, we are using the full precision, that is 32-bit floating point operations. But we can do some quantization, reduce the precision maybe to 8 or 4-bit, right? So to reduce the compute, also reduce the memory footprint. So to extreme case, we can have this binary neural network. So that is, you just using 1 bit, 0 and 1, or maybe -1 or 1 to represent the model weights, or the activation function, or maybe both, right? So that's can save a lot of computation and memory footprint. So as a matter of fact, in this direction, we have a recent work using neural architecture search for these binary neural networks. So that is published in IJCAI 2020. But is the efficient network the ultimate solution, right? So the traditional neural network, even for the efficient networks, so we have this efficient mobile net V1 and V2, they are all designed, or they can only execute at a specific resource constraint, right? So that is determined by the number of parameters and the flops the model has. But in real world applications, we have diverse or heterogeneous devices that has different computing resources, right? We have these desktop grade GPU, we have mobile phones, maybe we have even smaller like microcontroller, right? The computation resource is very limited. So a single network is not able to optimally fit all these diverse hardware platforms. Even if we only consider just one single hardware platform, let's just consider a specific platform like iPhone, maybe iPhone 10, right? The computational resource is also dynamic on the single platform, right? These can be affected by the battery, right? You have a full battery, maybe a very low battery, 10%, or even a smaller, lower battery condition. And also the workloads. Maybe at some point, you only have one application open, right? So you have all the memory and computational resource for this application. But at some point, maybe you open multiple applications, then these resources has to be split among all these applications. So these resource budgets are dynamic. So then the research problem is gonna be giving these dynamic resources, how to instantly, adaptively, and efficiently trade off between accuracy and computational cost for neural networks at runtime, right? So at the inference time, we want to instantly trade off between accuracy and the latency. So towards solving this problem, I'm going to present our recent work that is published in ECCV 2020 as an oral presentation. So we developed this mutual net, adaptive conv net via mutual learning from network width and the resolution. So now you know the problem we want to solve, that is, how to cope with this dynamic resource to achieve trade-off between accuracy and efficiency. And one possible solution, or maybe the straightforward solution, is we can install all possible model variants that has different resource and accuracy trade-off in the AI system or devices, right? For example, we can install multiple different models like ResNet, maybe a large model, and then we have a smaller, an even smaller model, MobileNet V2. And then, when the resource budget, changes, then we can switch among these different models. And maybe we can also, using pruning method, right, to prune a full network into different ratios and install these different pruned ratio, model variants in the device and switch among them according to the dynamic budget you have. But you can easily see this is not a very good solution, right? There's a couple of problems. So one is it will consume more memory and storage, right? You have to deploy multiple of these models on a single device. And definitely this is not scalable, right? So can you install like hundreds of these models on a single device to, to achieve this kind of fine-grained computational level? So a better solution is these dynamic neural networks. So it is able to changing the network structure during the inference time. So slimmable networks is one type of these dynamic neural networks. So the idea is that slimmable network is able to slim the network width. So the width means the number of channels in the neural network layer. So this is here, as figure shows, this is the full network, and we can slim this full network into a subnetwork, smaller one, according to some slimming ratio. And this is another one with a larger slimming ratio. Okay, so by sampling these subnetworks during the training, and the network is able to achieve, able to run at different width to achieve these kind of, or to meet different computation budget. But on the right side, as you can see, the performance drops significantly when the computational cost become very low, right? So under 100 millions flops. So the performance drop a lot from around 60% on the Imagenet top one accuracy to close to 20%. So this is not good for some of the real world applications. But if we take a close look at the computational cost, how it is computed for one layer. So it actually determined by the network scale. So that is the input channel and output channel, as well as the input scale, right? The height and width, for example, your input image size. And assuming we have a fixed size kernel k by k. So actually you see there's two important factors, the network scale as well as the input scale that is affect the computational cost. But for the slimmable networks, apparently they only consider this single network scale, that is by changing the width of the network, but totally ignore the input scale. So our goal is trying to take these two factors jointly or simultaneously into the network design so that we can achieve a better accuracy and efficiency trade-off. Another plus is that if you think about different scales of the input, we can learn multi-scale representation so that your representation learned can be better. To do so, here I show the overview of the proposed method, the mutual net. So in each of the iteration, we will have a full network. So full network here, I mean, this is the width ratio, 100%. And this full network will be fed with the original input resolution, 224 by 224. And at the same time, we will also generate subnetworks. So in this particular example, I show 3 subnetworks. Okay, so we'll specify a specific subnetwork lower bound. Okay, so in this example, we specify 25% of the full network is the width lower bound. Okay, so these 25% is sampled by just pick or sample the first 25% of the channels for each of the layer, as you can see illustrated from this here. And the other 2 subnetworks will have these random width ratio, alpha 1 and alpha 2. So these ratio is going to be a number between the lower bound 0.25 and the upper bound of 1. So in this case, if we randomly sample these different ratios, we are able to cover all kinds of width configurations. So that's the subnetwork generation. So once the subnetworks is generated for each of the iteration, and we will, each subnetwork will select a random solution from these resolutions you can specify, right? 224 is the original resolution, and we can downsize or resize image into a couple of different sizes, smaller ones. And each of the subnetwork can randomly select one resolution from the input scale choices here. So to train the network, we'll have for the full network, we'll have the usual cross entropy loss using the ground truth labels to compute the loss. But for the subnetworks, we're using the KL divergence. So basically, we're using the output of the full network, so it can be considered as the soft label, and we're trying to make the subnetwork generate output match the output of the full network. So you can using the ground truth for the subnetworks as well, but experimentally we found using the soft label using KL divergence loss perform a little bit better. So this can be explained so this soft label can be considered as a label smoothing that usually able to help the model training. So the total loss will be the loss coming from the full network, as well as the loss for all these subnetworks. We sum them together. So how does this mutual learning works? So let's look at the gradient and then do some analysis. So for illustration purpose, let's just consider a simple case. We have 2 subnetworks, one with the width 40% and the other has 80%. And we only have 2 resolution options, 128 and 192. Okay, because of the loss accumulated during the training in this mutual net, And the gradient also coming from different parts. Specifically, let's look at the subnetwork 0.4. So it has the gradient coming from itself, right? So this is the gradient coming from itself, 40% subnetwork. But at the same time, it also have the gradient coming from the other subnetwork, which is 80%. So the first 40% of these 80% subnetworks is also going to be added to this 40% subnetwork. So there is an overlap region. And these 14% subnetworks is actually able to learn multi-scale representation. So the one scale is coming from the network scale because we have the 40% subnetwork. We also have the gradient coming from the 80% subnetwork. At the same time, we also learn from these multi-resolution representation. So that's from the input scale, right? Because the 40% subnetwork using its 120 image size, but for the 80% subnetwork, we're using this 192 resolution. So as you can see, the knowledge from different subnetworks and also from different resolutions all shared among these different subnetworks because of the weight sharing mechanism among the subnetworks. So if we adding more subnetworks, as you can see here, we're adding more terms here, the gradient coming from other subnetworks and other resolutions. So for the resolution, if we have a fixed kernel size, definitely if you have a smaller image size, for the same kernel size, maybe you are able to see wider context so that your network is able to learn this kind of multi-scale representation. And once the network is trained, we are able to test at different configurations. So we can actually define a width interval. For example, we have the full width resolution 100%, maybe the interval is going to be 5%. So we can have a grid of width. And also we can combine it with different resolutions. So for each of the configuration, so for this particular MobileNet V1 backbone, we can compute the corresponding computational cost and the millions of floating point operations for each of the individual configuration. So we have a table for the computational cost. And for each of the configuration, we can inference the network we just trained, right? Inference can be very fast. So we just have to do this inference for different configurations. And we can also generate a table that is list the accuracy corresponding to different configurations, okay? So when you deploy this model, okay, let's say at this point, I have the computation budget is 600 million flops. Okay, so we look at this computation cost table, 600 million flops. So it seems like we can using the full network with the original resolution, right? It's still under 600. So this is the best configuration you can have to achieve that, the best accuracy. But at a certain point of time, the computation budget reduced to maybe 500, okay? Then we can look at this computation cost table, okay? If my budget is 500, then essentially, any cost is below 500, we can use it, right? Because it does not exceed the computation budget. But what is the best one? So the best one would be this, right? 466 is going to be below the 500 million flops budget, but in this case, we'll have the best accuracy. So basically, we can look at this table and figure out at a specific computation budget, which configuration is your best option. Of course, you can using maybe more fine-grained interval to get more configurations so that you are able to trade off the accuracy and the computation cost at the final level. So if you know a specific computation cost level you have, and you can actually first go through these accuracy table and figure out which configuration is the best under a specific computation cost level. So then we can, kind of formulate or generate this query table. So during deployment, we only have to deploy a single model. So you mutually trained a single model, and based on this query table, you can figure out which configuration you can instantly select to meet that specific budget. We did experiment first on the Imagenet classification. So Imagenet dataset is a large-scale dataset for image classification. And we compare our mutual net with this slimmable network, which only consider the network width as the trade-off factor. As you can see here, under very low computation budget here, the improvement is significant, over 10% improve under this very low computation budget. And also, we did another baseline using MobileNet v2 at backbone, and the similar trend can be observed. So our method is consistently perform better over the Slimmable network. One thing to note is that because this ImageNet is a large-scale data set, even a 1% improve can be considered as a considerable improvement. And we also did some comparison with individually trained network, right? So we can maybe specify individual configurations and train the network at that specific configuration. So we did this for MobileNet v1 and then v2. So at each configuration corresponding to a specific computational cost, we train the MobileNet from scratch and see what is the performance looks like. And our mutual net, which is training a single network one time, is able to outperform these individually trained network at a specific configuration. And this is, we have observed a similar improvement over the MobileNet v2 backbone. And this figure shows how this mutual net is able to achieve a good trade-off between the network width and the resolution. Okay, so this dashed line shows the universal slimmable network, so which is only considered the network width. So in order to achieve, to meet the reduced computation budget, you can only slim the network's width, right? To keep reducing, to drop the network width to meet that reduced budget. But for our mutual net, because we are considering another factor, which is the input scale, we can achieve a better balance, right? So in the beginning, we are using the full resolution, 124. If we keep decreasing the computational cost, then we'll reduce the resolution. And within the same color is going to reduce the width. Okay, so as you can see from this curve here, we are able to achieve much better job at the lower computational cost side. Okay, so the US Net Plus is actually our strategy trying to do a simple strategy to improve the US Net. Basically, we do this, we test this US Net at different resolutions and see at a specific computational cost, which one give the best result. So that's a very simple improvement over US Net. But still, this method only consider this resolution during the testing. So they are not doing the mutual learning during the training. So the performance is still worse than the mutual net. We also conduct experiment for other tasks like object detection and instance segmentation on this COCO benchmark. And similarly, our mutual net is able to consistently outperform USNet at the entire accuracy and the FLOPS spectrum. And this is the same for the instance segmentation in terms of the mask average precision. And this figure shows some of the qualitative result for the object detection and the instance segmentation. So here is the mutual net. We are able to detect more small objects and identify some of the object and successfully doing the segmentation. And the code is publicly available. So you can try this mutual net to achieve this kind of adaptive neural network. And we also extend this mutual net training into 3D convolutional neural network for video analysis. So for the video analysis, we are dealing with videos, right? So we add an extra dimension of time. And 3D convolutional neural network is going to be even more computational expensive. So we want to also try in this kind of mutual learning strategy on this 3D convolutional neural network. But we have to pay attention to specific designs for these 3D convolutional neural network. It's not just naively adding an extra dimension of time during the trade-off. So for example, for this, one of the state-of-the-art 3D convolutional neural network for action recognition is the slow-fast network. So basically it will have multiple pathways. So here we have fast pathways, operating at a higher sampling rate, but with a very small network in terms width and depth. I also have another pathway called slow pathway that is operating at a lower sampling rate, but for lower resolution, but the network is going to be wider and deeper. So is it's the best way to do this kind of trade-off on both pathways. And in this paper, we found out it's not necessary to, or maybe it's not useful to trade off on the fast pathway because it's already going to be a smaller network. And this fast pathway has the benefit of capturing complementary information to the slow pathway. So we kind of, tailor this kind of mutual net learning framework for this specific multi-pathway strategy and to achieve the better trade-off for the video action recognition. So the paper is online on arXiv. So if you're interested, you can go through the details in this paper. Another research extension is we want to also explore this efficient distributed training. For example, this federated learning paradigm. So for the federated learning, the goal is trying to preserve the privacy of the data, right? So a lot of time, the mobile device user, they don't want to share the data across different devices, but we still want to leverage these huge amount of data. So for the federated learning is that these local devices will deploy the same model and as the global server. So the local devices can do the training locally with their local data and then sending their model weights to the server, okay? So the server then will aggregate the weights coming from all these local devices and do a global update, okay? So that updated model will be sent, the weights will be sent back to the local devices so can facilitate further training. Okay, so you can easily see there's gonna be a couple of problems, right? Because the devices, distributed may have different computing resource, right? Cell phones, iPad, etc. And if we deploy the same model here, and some of the local training will be very slow, right? For some of the resource limited devices, we call this slow worker, okay? And then the global model on the server has to wait this slow worker to finish the update and sending the weights to do the aggregation. Otherwise, it will have to discard this local device, right? Another thing is, since we are sending the weights to the server, the communication bandwidth is also plays an important role, right? For some of the regions, maybe you have 5G, but for some of the regions, maybe you don't have 5G, only have 4G or 3G. So the sending a lot of large model weights also take a lot of time, right? This is not going to be efficient for this federated learning training. So we can apply this kind of dynamic network strategy by deploying different network architectures, right? This may have the full network. I mean, 50% of the network, maybe this is 75%, and this is 30% of the full network. And also considering the communication bandwidth, maybe we can do further quantization, right? Maybe here we quantized the weights or into only 4-bit to facilitate the communication aspect. So in this case, we are able to encourage efficient learning over the air. So that's for the federal learning paradigm. And this is an ongoing research here. Next, I also want to talk about another piece of work that is a new regularization method for training deep neural networks that is inspired by this mutual learning paradigm, and it is published in Europe's 2020. So the motivation is this for the human perception, right? So we are able to recognize, different augmented object or image. So for this dog, if we rotate multiple orientations, we are still able to recognize this is a dog, right? So for aware generalized network, we want the network have the same property, right? That is going to be robust to these augmentations of your data. And also for aware generalized network, its individual neuron may be able have a very strong representation capacity, right? They're able to recognize the object very well. So that means if we sample the subnetworks, the subnetwork should also perform well on a data set to recognize the images or objects at a high accuracy. So these motivate us to using the subnetworks to improve the representation learning of the full network. So the structure is similar to the mutual net. So again, we will have a full network. So the full network will be given the original image, okay? And we're also using the subnetworks. So we also randomly generate the subnetwork by slim or by sample the width of the full network. And this subnetwork will also be given different augmented images with different augmentations. You can do resolution scaling, you can do rotation, you can add in noise, or maybe you can do a combination of these different transformations and send these input to the subnetworks. And the weights will be shared among the subnetworks as well as the full network. Okay, and the loss will also occupy two parts. One is from the full network, and the other part will be the summation of the loss of the subnetworks. Okay. So since the subnetworks are part of the full network, right? So we are sampling the width of the full network, and we do this weight sharing scheme, and we can call this subnetwork parts as the self-guided augmentation or perturbation to the gradient of the full network. Okay, so here is the gradient analysis of this our grad-aug approach. So this is the gradient of the full network, and this is the gradient coming from the subnetwork. So if you think about other structure regularization technique like dropout, right? Dropout, you randomly disable some of the neurons in the network. You can consider that is adding some random noise to the original network. Okay, so because we're randomly disable some of the neurons, so it functions like adding random noise to the original gradient. But for our approach, grad-aug, we are actually adding meaningful perturbations to the raw gradient, right? Because this is the subnetwork, they share is part of the full network. So it is able to reinforce some of the good descent directions, okay? So that is able to improve the performance. And we conduct experiment first on image classification, and we are compare with some of the leading regularization technique, both from structure level as well as data level. So for example, the cut mix. So here, if you don't know what cut mix is, so here I just give you a graph illustration. Basically, you have two images, and you can, for one image, you can cut out one piece, and maybe take another patch from the other image, right? The cat, and piece them together. So basically you cut one patch and mix with another patch. Okay, so this is the data level augmentation trying to, force the network pay attention to other regions, you maybe more learn diverse representation of a specific object. And as you can see here, our approach, GradOrg, is able to perform better than all these leading regularization technique. Okay, cut mix and these kind of structure regularization method, draw block, stochastic depth, and draw path. As I mentioned before, the transformation of the subnetworks can be arbitrary, right? You can have a single transformation, maybe you can have a multiple combination of transformation. So our method is considered as the structure level regularization. So it's kind of orthogonal to these data level regularization. So one thing we did is we take the best data level augmentation, cut mix, okay? We take this as the transformation strategy and then combine it with our subnetwork. So we have this GradOrg plus here. That means we take the cut mix augment image as the input to the subnetworks. As you can see here, able to further improve the performance, almost reach 1% improvement for the top one accuracy. So what do this full network and the subnetwork learn, right? If we're using this kind of mutual training, using this subnetwork to regularize the learning of the full network. So we do some visual explanation and what exactly the subnetwork and the full network learn if we do this kind of GradOrg strategy. So on the right side, this is the baseline. So that is just a single original network and train on the data set, and that's it. And we're using this class activation map to visualize the attention, the network has been paid to. So the class activation map, basically, if you make a prediction, this is a dog, it is able to tell, how much contribution each pixel contribute to this decision. This is a dog, okay? So more red indicating the network is paying more attention to these pixels, means these pixels contribute more towards the decision of making a prediction of dog, okay? So as you can see here, these attentions kind of focus on the body area of this, the first dog, the dog on the left, okay? And we also do the examination on this GradOrg trained network, right? In the GradOrg, we have full network. We also have the subnetwork. So for a simple case, we just sample one subnetwork with 90% of the width. And we examine using the class activation map for both full network and subnetwork. So as you can see here, I highlight on this red circle, because the subnetwork are sharing the weights with the full network, right? So the knowledge are shared among full network and subnetwork. So the subnetwork here, paying attention to the face region of this left dog, and you can see this translate to the full network as well, right? Because they are sharing the network weights. So the knowledge are shared. So the full network is also pay attention to the face region of this first dog. But because the full network also have 10 additional % of the weights as the subnetworks, right? It can leverage that to learn additional content that is helpful to determine the image containing the dog. So that's why you'll see this yellow circle region, right? So we also have a red color region that is paying attention to the second dog, the one chasing the left one, right? But for the subnetwork, we don't see this red region, right? But for the full network, it is able to using that 10 additional % network to learn this kind of diverse representation. And here is another case for recognize this is maybe a tissue box. And we did some ablation study because we, for this training paradigm, we have to generate a number of subnetworks. So, and also we have to specify, what is the lower bound for this subnetwork, right? So these are the hyperparameters we have to consider. So we did this ablation study, trying different numbers of subnetworks and using different width lower bound to see how they affect the performance. And we also analyzed the contribution of individual component, right? We have the different input scale, right? So that's one type of augmentation. And also we have different width to generate the subnetwork. So we remove one by one. So we first just don't consider random width. So basically we have subnetwork have the same width, but input different input scales. And this is the accuracy we get as compared to the baseline. So it is able to improve the performance because of the kind of multi-resolution training. But if we input the same resolution, but using different subnetworks, we able to improve the performance, but not a lot. But for the grid org, is basically we are having these two components together is able to improve the performance by using them individually. Also, on the right side of this table, we also show the impact of different transformations. Okay, so we tried using different input scale or resolution. We also try different rotations, like 90 degree, 180 degree, different rotation angles. And we can also do a combination of these two transformations, right? First, resize the resolution, then rotate the image and see what is the performance impact. As it turns out, a simple resolution scale is able to achieve a very good result. So just to keep it simple, we're using the resolution scale in the grid org approach. And we also do experiment on some the downstream task, like the object detection and the segmentation. And we also compare with other approach. So here is the cut mix and mix up. So for these approaches, they are not able to directly train on this kind of detection task. Because if you think about, if you cut mix, right, that image, how do you specify a label after you do this cut mix, right? You have part of the cat, part of the dog. How do you mix up the label? That's very difficult to specify a label, right? Also for this mix up, if you mix up two images, how do you specify this pixel belong to the category of cat or dog if you want to do semantic segmentation? But for our case, because we are just regularized from the network structure perspective, we are able to directly train the grid org on this detection data set as well. So for this, if we're using this these other technique pre-trained model and apply that fine-tune it on this detection data set, is able to improve the performance very marginally, right? You can see here only 2%, 1%. But for our approach, we are able to improve 1.2%. So this is using the Imagenet pre-trained. But if we're directly using the task-specific data set for the training, we are able to further improve the performance. And this is a couple of visual examples to show our grid org approach is able to detect more objects and do more better job on the instance segmentation. And this is another example. So for this one particularly, is not able to detect any of the object for the baseline, but using the grid org regularized training, it is able to successfully detect these two horses. Okay, so for the overfitting problem become more severe when we dealing with limited training data, right? So we need to have better regularization strategy to learn better representation of the network. So we also conduct experiment under this low data regime. So basically we are using a small training size. So for the Safari 10, we have 220 training labels, which is much less than the normal training number of samples. And compare with other regularization technique, grid org is significantly performs better than the other regularization technique. So as a matter of fact, other techniques is kind of hurting the performance, right? So for this cut mix, the reason is that under very limited training sample, if you also do this kind of strong augmentation of the image, is kind of introducing noise, right? Because you don't have a lot of clean labeled data. clean samples. But if you do this kind of more rigorous augmentation, it will hurt the performance and hinders the learning of your model. And we'll also test the robustness to the adversarial attack. So by adding some adversarial perturbation to the original image, we want to see if the regularization technique is able to make the model more robust. And for the GradOrg Plus, that is using the cut mix as the data transformation methodology, we are able to further improve the robustness of the model. So under different levels of the attack severity. Okay, so again, the code for the GradOrg is online. So you're welcome to try this org as the regularization technique for training the network. Okay, so a couple of reference mentioned in this talk are listed here. And I also want to thank NSF Intel to support this research. So these research are sponsored by these or supported by these two grants. Okay, next I want to touch upon a little bit on my future research agenda. So there is a couple of directions I want to explore. So first one is the efficient machine learning via the algorithm and hardware co-design. Okay, so obviously, we can develop efficient algorithm, but we cannot overlook or ignore the hardware side, right? A lot of network you develop may not be optimal for a specific hardware, right? So you may optimize for GPUs, but this kind of architecture may not be optimal for hardwares like FPGA. So we have to consider both sides and trying to do this kind of co-design so that we can unleash the power of both sides. So I want to, using the auto machine learning technique, trying to auto-generate some of efficient neural networks there and their hardware implementation so that you can have more compute per unit. And also I want to pay attention to energy efficient algorithm and hardware co-design. Okay, so as a matter of fact, a lot of energy or power has been spent, has been devoted to AI research, right? So that caused a lot of green gas emission. But on the other side, if you think about how our brain works, right? Our brain is able to work or do complicated computation at ultra low power, right? So I want to explore this direction by using some brain-inspired network, specifically these spiking neural networks. So typically the spiking neural networks works, take this kind of spike signals, and once the membrane reach a certain threshold, a neuron can fire, okay? And also this can be combined with the brain-inspired hardware, like the neuromorphic hardware. For example, the dynamic vision sensor or the event camera. So by combining these spiking neural networks and these kind of neuromorphic hardware, we are able to achieve energy efficient algorithm. And a second direction is, developing agile intelligence for this complex connected system. So now we are in the age of, thriving 5G and AI. So a lot of devices has some AI capability and they all connected to each other, right? Those drones, smart connected vehicles, robots, service robots, etc. Right? Imagine you have maybe a service drone, maybe from Amazon, they are trying to deliver packages, figure out what is the best navigation route to do the, to deliver the package. So there are two fundamental tasks I want to explore. One is how can the AI network architecture, adaptively transform to share knowledge with each other, right? So maybe this specific device has one type of network, but the other device maybe have another type of network, but how they are able to share the knowledge among each other. And the second task will be, because we are dealing with this kind of large scale connected system, and each of them may have their disparate training data or semantic labels, right? How can we combine them together, kind of to form like a core vision system, right? That is able to adapt to different tasks or to different environment. So these research require some of the novel solutions from many, machine learning or vision topics like self-supervised learning, lifelong learning, or open set learning, federal learning, domain adaptation, etc. And finally, I also want to pay attention to applications to in healthcare, smart manufacturing, and STEM education. So these different applications, they have their application-driven insight and the challenges. So how can we build machine learning algorithm and system that is specific tailored to the specific needs or challenges for these applications? And also want to develop personalized computer vision or machine learning solution for these applications, right? So in the healthcare, if you have this kind of, want to develop these personalized treatment for individual patient, right? And also during the pandemic, because we are, everyone is doing this online learning. So makes me thinking how we are able to develop, personalized AI system that is able to help student, maybe they have different learning progress at different learning stages, how to develop this kind of personalized AI system to help them to learn better. So these are the third direction I would like to explore as my future research. So there are a couple of funding opportunities. So for example, the NSF National Robotic Initiative 3.0 this year. Also try to apply NSF Career. And of course, the SCIENCE core program and the cyber physical system, smart and connected community, real-time machine learning. So these are all very good programs. I see my research will fit. And also some other funding agencies like DARPA, IARPA, ONR, Air Force Research. Okay, and also I'll try apply fundings from industry. So I already mentioned that we have one ongoing research that is sponsored by Intel. So I think, we are building good relationship with Intel, and there is going to be potential more funding opportunities in the future. And also maybe, by student doing the internship, we can, establish connections with other different industries and see if there's other funding opportunities like gift fund, etc. And also some of the companies will have faculty research award like Google, Amazon, Facebook. So those are also very good opportunities. I want to maybe apply for those awards. In terms of teaching, I have a teaching experience both in the undergraduate level and the graduate level at the UNC Charlotte. So I actually developed a core course for the undergraduate level that is Introduction to Machine Learning. So we are actually developing this machine learning concentration in our department. So this is the core course for the machine learning concentration. So I developed from scratch. Also, this is a graduate level course that is for deep learning in computer vision. And also applied AI is also another graduate level, although it is in catalog, I developed from scratch. At UCF, when I was a postdoc, I was teaching this robotic vision course in spring 2018, which is an online course. Different universities able to enroll in this robotic vision online course. So there are a couple of courses I'm comfortable to teach at UCF. So on an undergraduate level, so this robotic vision, algorithm for machine learning, artificial intelligence, I'm able to teach these courses. And also for the graduate level, so I think CS has this master in computer vision program recently. Then I'm able to teach some of the core course in this master program. And also I'm interested in developing new course. So based on my research, that is real-time machine learning, or at least incorporate some of my research component into some of the existing courses like machine learning or computer vision, just to let students to have some flavor, how you will connect these vision system into some of the real world challenges and how we are able to address that. Okay, thank you for coming, and this is all my presentation. If you have any questions, feel free to ask.
So thank you, Dr. Chen, for the wonderful talk. And I think we have few minutes left, and we can maybe first try to take questions from the audience. So any quick question for Dr. Chen?
May I have a question?
Yes.
Thank you very much for very interesting talk. I have a few questions regarding the first one is when you do the performance analysis,
Yeah.
In my understanding, you mostly rely on the accuracy metrics. Is that correct?
You're talking about the mutual net, right? Are you talking about the mutual net for this kind of? Okay.
Mhm.
So actually, we have so we have two metrics. So one is these floating point operations. So that is like the most commonly used metric for measure the computational cost. So under each floating point operation or computational cost, we want to measure the accuracy. So basically, under each of the computational costs, we're trying to perform better than the existing method, like this slimmable network.
Okay. Why you think that, let me ask it this way, why you think that accuracy metrics is the best metrics for performance analysis? Because we know from the theory that accuracy, say for example, your data is unbalanced, yeah, when you are detecting cats and dogs, for example. If you have 95 cats and 5 dogs, and you have the worst 95% accuracy, then it does mean that the network is performing well, correct? So therefore, probably, I mean, my question is why you think that for performance analysis, I mean, particularly for your study, is the best.
Yeah, so I think that's a good question. So definitely this kind of the class distribution, this kind of long tail problem is going to be an issue. But so here, because we want to evaluate, right, we want to competing with the other method. So we adopt some of the existing data set like the Imagenet. So for this Imagenet, maybe we don't see that severe like this data unbalanced issue. And if accuracy is the best measure you can use, and of course, for all the method, we are using the same metric, right? So under the same metric, our performance, our work has the better performance. But of course, for the later or other applications, if you have those challenges you are mentioned, maybe we should also consider other evaluation metrics to kind of address those challenges.
Yeah, thank you very much. Absolutely. I mean, your research is very production oriented, and this is really cool. And the academia is completely different from production. And when you deal with the production, you probably might not want to use something fancy, but rather some robust networks. Like, for example, you would prefer simple VGG16 instead of something like, for example, capsule network, right? So my other question was, how do you, is there any effect of those subnetworks on the pose problem?
You mean what do you mean, like the
Yeah,
pose
the pose is all we are doing here, in my understanding, is just modifications of CNNs, right? Convolutional neural networks.
Yeah.
And convolutional neural networks fail detecting. Let me give you a very simple example. Say, for example, you have a face, and you actually don't have a face. You have features of face. You have eyes, you have nose, you have mouth, and all those features are kind of scattered. Okay, they are messed up, just they're mixed. and convolutional neural network fails to detect such kind. CNN is okay with rotation, okay, but for the pose problem, it has big issues. So when you give this example to convolutional neural network, it still detects it as a face. However, it is not. So what I wanted to ask is any chance of subnetwork to resolve this problem?
Yeah, so I mean, it depends on your application, right? Like you said, if convolution neural network is doing a poor job on your specific application that is pose estimation, maybe you prefer using some other network like the capsule, or maybe even using the latest like transformers, or maybe graph neural networks. Then the general training paradigm still applies, right? It's just you have to figure out, if you want to achieve this kind of dynamic networks, what is the network you want to use, and what is the trade-off dimension you want to use, right? So maybe for the graph, or maybe for the transformer, let's say, for example, maybe you don't want so many transformer and multiple head for the self-attention, right? Maybe you can remove some of the head for your attention, or maybe for your graph neural network, you want to remove some of the connection in your graph. So those are the dimensions you can think about to trade off between accuracy and efficiency. So, I mean, the network, the framework is general, can be applied to any of the network, but how you train, what kind of dimension you want to trade off, that is going to be specific to the network you are selecting, and that is going to be specific to your applications.
Thank you for this question. The other question is, when you refer to pruning, I came late, and I apologize for that. I didn't catch the difference between the mechanism of between these subnets and resnets. Is there a chance to quickly go through that?
Sure. So pruning, like I said, so pruning, so basically you want to is just reduce the network size, right? To have an efficient design. You can prune, then typically you need to retrain it to achieve the same level of accuracy, maybe. And also pruning, there's a lot of techniques in the pruning. You can do structured pruning, you can do unstructured pruning. Okay, so there's a lot of method to do the pruning. But here, we are just take the very simple structured pruning. The subnetwork generation can be considered the very simple structured pruning method, right? You just take whatever the first 20 or 30% of each of the layer, the channels of your layer. So that's very straightforward or simple way to generate the subnetwork.
That's sort of dropout?
Yeah, you can consider that's a dropout, right? You drop the entire channel, right? So here you have 100 channels, then maybe I just take the first 20 channels, right? We have a ratio of 20% of the network, right? So you can consider like you drop the entire channel. As a matter of fact, we are working on an improved version. We call it MutualNet V2. So definitely we didn't consider the subnetwork, right? We are just using the very basic, simple, selecting the subnetwork. We considering these kind of pruning technique. One way is how you generate the subnetwork. We can using different pruning ratio to generate better subnetworks. Or we can using some, the recent lottery ticket hypothesis, right? Without training or pruning, right? We can using the lottery hypothesis generate very lottery tickets, which is smaller network, but also have very good performance, and using them as the subnetworks so that you are able to achieve better performance. So we actually have some result on this improvement, and is able to improve this MutualNet over 1 or 2%. So that's a good question. So we're actually working on this direction.
Thank you very much. Hope and wish.
So we are almost out of time now. Sorry, Mary. So any last question from anyone else from the audience? We can quickly take that before we end. So if not, like I have a quick question, Dr. Chen.
Sure.
So for like 2 or 3 of your methods where you're trying to like use the subnetworks, the optimized version. So you showed results where your network was able to detect like smaller objects, right?
Right.
So I didn't quite get it. Like, what makes your network spatial so that it's like able to detect those smaller objects? Is it
Yeah.
just like trained on different resolutions, or is it something more than that?
Yeah. So one aspect is coming from different resolution because we have different input scale, right? So
Hmm.
if you don't, if you have a small resolution, maybe you'll see more context, although maybe the object information is kind of even smaller, but maybe you are able to comprehend some of the, context around that object to make you, have more like context aware so that you are able to detect those objects. And because those subnetworks, they are sharing the weights with each other. So the knowledge between different subnetworks is able to, transfer among different subnetworks. So that is part of the reason the representation, the mutual net learn can be better.
Okay, all right. Thank you. So, Dr. Abhijit, so we have a different link for the next meeting, or should we end this talk here? How would you like to proceed?
Yes, so we have that other link. I think we can go to that one for the following meeting.
Okay, so in that case, so let's thank the speaker once again, and thank you very much, Dr. Chen, for the wonderful talk. So we can end the
All right, thank you.
talk part here, right?
All right, thank you.